Yeah, so I will talk about the Brouwer-Kakutani's fixed point theorem. So there are two theorems actually. That is not the, I mean, a single theorem. There are two theorems. One is for, I mean, just a normal function, normal mapping, and another is for point to set mapping. So there are two theorems I will discuss: Brouwer and Kakutani's fixed point theorem, and some of its application in game theory. So in the application part, I will not be very detailed. I will only give some rough sketches about, I mean, how can possibly be this kind of theorems be useful in some game theory problems. So that will not be very detailed. Only rough sketches will be there. Yeah. So let's see. So Brouwer fixed point theorem was one of the early achievements of algebraic topology, and is useful for proving many other important theorems. The case n equal to 3 was first proved by someone called Piers-Boel in 1904, and later Brouwer gave a proof in 1909, and finally Hadamard came with a proof in 1910. And in that year, actually, Brouwer gave a different proof of the fixed point theorem. Actually, so in the literature, there are many proofs. I mean, which uses a wide range of ideas. I mean, some proofs use some differential topology tricks. There are some combinatorial proofs. There are some proofs using Stokes theorem. So there are various theorems. But today, the proof I will give, that is based on, I mean, just basic homotopy theory, is basic algebraic topology tools. And as an application of Brouwer's fixed point, we will prove Kakutani's fixed point theorem. So let's go to the Brouwer's fixed point theorem. So, so let's say in the Euclidean space you have an n ball. Okay. So let's say your n is equal to 2. So you have this closed ball in R2, and then you are looking at a continuous map from this closed ball to this closed ball. And then Brouwer is saying that this map will have a fixed point. So by fixed point, we just mean that there is a x such that there is x naught such that if x naught is equal to x naught. So that is what we mean by a fixed point. And Brouwer fixed point theorem is saying that whatever continuous map I have from this closed disk, from another closed disk, that will have a fixed point. And later you can easily check that, I mean, you can replace this closed set by any closed bounded convex set, because they are of same homotopy type. So we will just restrict to the proof where this set is exactly a closed ball. So yeah, so let's see the proof. Okay. So for some motivation, I mean, first look at the n equal to 1 case. So in one dimension, you can just replace the closed ball by your 0-1 close interval, right? And then we already showed in class that every continuous map from 0-1 to 0-1 has a fixed point. And that is just a very basic application of intermediate value property. So given a f, you define another function g, fx minus x. And from intermediate value property, for continuous functions from a connected space to ordered space. So remember, when you have a connected space in the domain, and then you have in the codomain an ordered space, and then you have a continuous function, so intermediate value property applies. So from that, the n equal to 1 case is very trivial. Okay. So now here is the interesting part actually, in which I will use the basic homotopy theory. So for n equal to 2, so this is just a, I mean, closed disk in the plane, right? So this is just a closed disk for n equal to 2. Right. So we want to prove that any continuous map has a fixed point there, has a fixed point. So I will just draw something. So what's the idea of the proof? So So by contrary, assume that you don't have any fixed point. So whatever x you take, the map f takes it to a different point. So by contrary, we are assuming that whatever x you take, fx is not equal to x. So for every x in the disk, you get a different point fx. So now what you can do, you can draw a ray from fx to x and extend this ray until it cuts the boundary of the circle. So you have point x, you get another point fx. You draw the ray which is in the direction from fx to fx, and you extend this ray until it cuts the boundary. So it gives a point, let's say phi of x. So depending on f, you get another map which is actually from the closed ball to the boundary of the closed ball, right? I'm mapping it to the boundary. So this is the idea of the proof, and then we will look at the induced map of fundamental groups. From there it will be very clear. Okay. So this is what I have written. Suppose phi is a map from B2 to B2. It's a continuous map, and assume there is no fixed point x, so that that is there is no point x so that phi x equal to x. And then you look at the ray joining phi x and x, and suppose this ray meets your S1, that is your boundary of the closed disk, that is just the circle. That ray meets your circle at some point, say Lx phi, and by that you have a map from B2 to S1. So this is your closed disk, and from here you get a map to the boundary of B2, which is just the circle. Now observe one thing, that this map actually fixes every point on the boundary. Isn't it true? If you look at this map actually fixes every point in the boundary. Because if you have a point in the boundary and f takes this point to some other point, then you join this line, so you create this ray, and that will hit the circle at this point itself, isn't it? So basically you have a retraction, right? So this S1 is a subspace of my closed disk, and this map is fixing every point on that subspace. So this map is basically a retraction. So now what happens when you have a retraction in terms of fundamental groups? So there is a standard exercise you
How
can
will we show that?
Yeah. Tell me.
Oh, I think you are going to show it is continuous. I mean,
Yeah. I mean, it's obvious that it's continuous, right? So should I just justify that? Yeah. Because if is continuous,
okay.
and also when you join that line, so that is also a continuous function, right? I think that is obvious. So I'm not rigorously writing that down. Yeah.
Okay.
Yeah. Yeah. So suppose your A is a subspace of X, and you have a retraction from X to A. A is a subspace of X, and you have a retraction from X to A. So then what you do? You look at the canonical embedding of A into X. That is the natural embedding, because A is a subspace of X. So suppose this embedding is I, let's say, and then you have this retraction A, which is R, let's say. So then you know that this R compose I, that is just the identity map, right? So we have this natural embedding of A inside X, then with the retraction of X into A, then R compose I is just identity on A. Now, if you look at the induced map, R compose I star, so that will also be identity. So from the functoriality property, this is just R star compose I star. That is also identity. And that will imply that this I star is in fact injective, isn't it? I mean, composition of two maps is the identity, so this map has to be injective. So that means my induced map I star from the fundamental group of A at a point say A naught to a point, to the fundamental group of X at the point say some A naught. This map is injective, right? So this is a general exercise. This does not have anything to do with the main problem. This is a general thing. Whenever you have a retraction from a bigger space into its subspace, then you look at the induced map of these fundamental groups. That will always be injective. So you use the same idea to the proof. Yeah. So that is what is happening here. So if you have this closed ball, then you have this boundary, which is S1, and this is a retraction. So then what happens? From the fundamental group of the circle, you get a map to the fundamental group of the closed disk. So, and that map is injective. We showed that this map has to be injective, induced map. So you have an injective map from pi1 of S1 based at x0 to pi1 of B2 based at x0. You have an injective map. But what is pi1 S1 based at any point, say x0? That is just integers. The fundamental group of the circle is basically integers. And what is this set? What is the fundamental group of B2 based at a point, say x0? I mean, just by observation, you can see that, I mean, that is just a trivial group, right? Yes, I mean, pictorially, even that is also very obvious. Whatever loop you have, you can just shrink the loop to a point. So the fundamental group of the closed disk is trivial, and fundamental group of the circle is integers. Now, can you have an injective homomorphism from a set of integers from the trivial group? That is completely absurd, because that does not even use any group theory. That is just a set theoretic argument. Z is an infinite set. This is a single set, singleton set. So you cannot have an injective map. So that is a contradiction. So
sorry to interrupt. Can I just make a comment about the continuity of this function phi tilde?
sure.
I mean, this just reminds me of your basic problem that I gave in the assignments, because you can see these lines as geodesics, and then because if it's continuous, your endpoints are going to converge. If you take a convergence sequence xn to some point x0, then fxn converges to x0.
Right.
So the endpoints converge and the geodesics will converge uniformly also. So you don't need that whole, I mean, this is like a big canon to solve a simple problem, but I'm just saying that it can be formulated in that way.
Exactly. No, that is actually very good, because we can generalize to the more general setting. So, I mean, fixed point theorem, I mean, arises everywhere. So in general, any geodesic space, you can talk about fixed points. So there it will be useful, obviously.
Okay, sorry to interrupt.
But I mean, no, it's fine. So I mean, so here I'm just taking my closed ball in the Euclidean space. So that is the most, I mean, obvious thing. So right. So yeah, so the proof is clear for everyone, right? This is just a basic application of fundamental groups, and we already calculated the fundamental group of the circle in the class. So
yeah, this is completely fine.
Yeah, right. So so the point is that now can we use this idea to go to higher dimensions? I mean, for 2-dimensional, this is fine. 2-dimensional, this is fine. But the point is that if you go to higher dimension, for example, n equal to 3, but then your sk is simply connected, right? We proved this in class that sk is simply connected for all k greater than or equal to 2. sk is simply connected. We proved that in the class using Seifert Van Kampen and identifying some other spaces with same homotopy type. We proved that this is simply connected. So from 3 dimensions, this pi1 sk based at a point x0, this fundamental group becomes trivial. So now you cannot use the previous argument, because I mean from a trivial group to another trivial group you have injective homomorphism, but that is not a contradiction. So for the remedy of this situation, I have to use you have to use the concept of higher homotopy groups, obviously. So like so we only learned pi1, like first homotopy group. So for every integer, for every natural number n, so you can associate a homotopy group called something pi1 x0, and then if you look at the nth homotopy group of this sk, then that will become integers, and then you can apply this argument. So I will not go into that, because since we have not done this thing, I myself also haven't read about this thing, the higher homotopy groups, so I will not go into that, but this is the idea basically. Okay, so
Oh, sorry, I'll just make a comment here about higher homotopy groups.
yeah,
So just if you look at the definition of higher homotopy groups, you just want to replace the unit interval. So when you consider you're considering loops for pi1, you want to replace it with kind of higher dimensional structure. So for dimension 2, you have disks, and for dimension 3, you'll have balls and so on. So what you want is because you have loops in for the first fundamental group, you are identifying the endpoints, right? So you are identifying the boundary of the one ball, so to speak. So so for higher homotopy groups, you have a map from higher dimensional disks, but then you want to identify all points from the boundary. Okay, so all the points from the boundary are mapped to just to one point. And then you can define the homotopy classes of such maps. Okay, relative to the boundary, exactly in the same way as path homotopy classes are defined, and then in the end you'll have a well-defined homotopy, well-defined group structure on this kind of structure. So the interesting part is that all the higher homotopy groups, so pi n for n greater than or equal to 2, they are all abelian, which is something really surprising. But the idea is that if you look at, for example, the square, okay, so for pi 2, you want to map the square. You want to have continuous functions from the square to your space, and you want to identify the boundary of the square to one point. You want to map all of the boundary to one point. Now, if you have so why is it abelian? So if you have two squares put together, then there is enough space to kind of rotate it and put one after the other. So if f and g are given by subsquares, then there is enough space in the square to rotate it. This is not possible with the line because there is no space to rotate things. So in everything in higher dimensions, n greater than or equal to 2 becomes abelian because there is enough space to move things around. These are just a couple of basic facts for higher.
I mean, I mean, in higher dimensions, many restriction goes away. For example, from R2, if you just delete a point, that is not simply connected, but in higher dimension, obviously, that is simply connected. Just remove a point from Rn. So it's something
Yeah.
like that. Yeah.
Mm.
Yeah. Like,
Okay, go ahead. Sorry to interrupt.
no, it's fine. So now we will prove the Kakutani's fixed point theorem. For that, actually, I need a trick, and this kind of trick is very useful in any combinatorial proof. So this kind of tricks completely lie in the zone of actually combinatorics. Actually, there is something called Sparner's lemma in combinatorics, which is very useful in proving many topological things. Sparner's lemma also use this kind of trick. So what is the trick? So suppose you have a simplex. Okay. So let's say we have a two-dimensional simplex. So I'm just taking it to be a triangle. So suppose S is the simplex. So let's call it S naught. I mean, now I will define something like S1, which is just what you call a simplicial subdivision, or more specifically a barycentric simplicial subdivision. So so we take the midpoints of every edges, and then you draw every medians actually. Every median of this triangle. So it's like this. Yeah. So what is happening is that your main simplex is getting divided into 6 more smaller simplexes. So from S1, I convert this S0 to this S1, and then you repeat this. You look at each of this triangle, and then again you apply the same trick. I mean, you draw the medians of the smaller triangles, and you do this for every triangle. You do this for every triangle. So you reach to S2. So you just continue like that. S0, S1, S2, S3, and so on. So as your n increases, your simplicial division gets finer and finer. So that is what I mean by barycentric simplicial subdivision. Why is it called barycentric? Because I'm just taking the midpoints of this edges, and then I'm drawing the medians. And what I'm getting is smaller simplexes, finer and finer simplexes. So it's simplicial subdivision. So that is what I will use for the proof. So some useful definitions before going into the proof of Kakutani's fixed point theorem. So suppose your S is a r-dimensional closed simplex, and let's denote this Rs to be the set of all closed convex subsets of S. Now a map phi from S to Rs is called upper continuous if some condition is satisfied. Okay, so what is the condition? So let me explain it. So basically your map is from Rs. So by Rs I mean set of all closed convex subset. This is a map. Okay. So what do I mean by upper continuity, or sometimes it's called upper semi-continuity or upper hemi-continuity, whatever you call it. So suppose you have a sequence of points, say x1, x2, x3, and xn, and so on, in your space A, S, and that converges to some point, say x0. And then your S1 is getting mapped to a closed convex subset of S, right? So suppose this is your phi of x1, then you have phi of x2. So this is phi of xn, and so on. And then what you do, you choose an arbitrary point, let's say y1 from phi x1, you choose y2 from phi x2, you choose yn from phi xn, And suppose this sequence of points y1, y2, and yn is converging to some point y0. Now, by upper semi-continuity, what we mean is that this y0 will also belong to the image of the point x0. So you can easily see that, I mean, this is just a generalization of continuity for point-to-point mapping. This is just a point-to-set mapping. Every point goes to a set. And by upper semi-continuity, what do you mean? I mean, you choose an arbitrary element from the set, and then, I mean, generalize the sequential definition. So I think the definition is clear for everyone, right? This is the definition of upper semi-continuity. Okay. So in 1941, I mean, Kakutani, I mean, came up with this proof, actually. So what he's saying is that, suppose you have an upper semi-continuous map, say capital phi, from S to Rs, be an upper semi-continuous map, then this map has a fixed point. Now, by fixed point, what I mean is that there exists a x0 belongs to S, such that your x0 belongs to phi of x0. So that is what I mean by a fixed point for a point to set mapping. You have to find the x0 so that x0 belongs to phi of x0 itself. So that is what I mean by fixed point. So if you have an upper semi-continuous map from a set S to the set of all closed convex of set of X, and we are assuming S to be a simplex, the closed r-dimensional simplex, then always you have a fixed point like this. Okay, so how do you do the proof? So I will just draw something. Okay, I have hello sir, can you hear me? Yeah, so so I have one problem, which is that I have 10 minutes time left. So I mean, after this meeting ends, I will send another link in the email. Is that okay?
Yeah, sure.
Yeah. I will send another link because I have a limited time. So
Okay.
yeah. Thanks. Yeah. So what you do is that you have this simplex. Suppose this simplex, and you have this. Yeah. So you have this simplex. And say these are the vertices of your simplex, say x0, x1, and x2. So this x0 is actually getting mapped to a subset of S, right? So remember, this is a point to set mapping. Yeah. So this point x0 is getting mapped to a subset of S. And your x1 is getting mapped to another subset, your x2 is getting mapped to some other subset, and then what you do, you choose an arbitrary point from there. Suppose you choose y0 from here, you choose y1 from here, you choose y2 from here. So so our goal is to define a point-to-point map from S to S. I have a point to set mapping, I want to convert it to a point-to-point map. So the way we do is that we map x0 to an arbitrary point of phi of x0. Similarly for x1 and x2. Now what happens is that I mean where do the interior point gets mapped? That you have to specify. So that is just the linear extension. Any point in here, any point inside this simplex, let's call it some z. That is obviously a convex combination of these points x0, x1, and x2. That is just a convex combination. So you map this z to the corresponding convex combination of y0 or y1 and y2. So your whole simplex gets mapped to something like this region. Yeah, so this is clear, right? I'm just
So not just a convex combination. I mean, you have a barycentric subdivision, which means that all the lambda i's are positive and they sum up to 1, right? So that's the simplex structure.
yeah, right. Yeah. So every point here can also be written as this combination such that lambda i's are greater than or equal to 0 and summation lambda I is equal to 1. So then you extend this map linearly to map this point z to some point here. So that gives a mapping, that gives a point to point mapping. So yeah, now observe that this is obviously a continuous map. You can easily check. So let's call this map phi1. So this map is a continuous map actually. And then you can continue like this. You create another subdivision, which is a finer subdivision of this simplex. Then you repeat this procedure. You get a map phi2. So this way you create a sequence of point-to-point maps. So that's the whole thing. Okay. Yeah. So that is what I have written here. Sn be the innate barycentric simplicial subdivision, and for each vertex xn of Sn, take an arbitrary point yn from phi of xn. Then the mapping Sn to yn defined on all vertices will define if it's extended linearly inside each simplex Sn, a continuous point-to-point map from S into itself. Yeah. Now we use Brouwer's fixed point theorem because I used it for circle, but similar argument also works for your closed simplex, at least in 2 dimension. So that is a continuous map from the simplex to the simplex. So by Brouwer's fixed point theorem, you have a fixed point. You have a fixed point for this map, phi n. So now this simplex is obviously a compact set, right? So obviously you can apply Bolzano-Weierstrass theorem that this sequence of fixed points, will have a convergence subsequence inside this, isn't it? It's just standard Bolzano-Weierstrass theorem. So for each map phi n, I am getting a fixed point. Let's say x suffix n. And that sequence of point will have a convergence subsequence which converges to some point x0 belongs to S. And as you can guess, my claim will be that this x0 is my desired point. X0 is the desired point. Yeah. So the idea is clear for everyone. I think.
Yeah.
Yeah. So I think I will just cut here and I will share a new link. So, sorry for the interruption.
So
yeah.
Sending it to the email, the IMS email.
In the IMS email, yeah, right.
Okay.
Okay. Sorry for the interruption.
See you in a couple of minutes then.
Yeah.